Hello, everybody. It is my great pleasure to welcome Adam Sikora from Buffalo, New York, SUNY, State University of New York. And he will indulge us with knot theory, with examples, and with operator algebras, and a tad bit of physics, if I understand correctly.
Correct.
Okay, Adam, the floor is yours, the Zoom is yours. Take it away.
Thank you, Piotr, for inviting me. It's a pleasure to be here at Banach Center and in Warsaw, my hometown. So the story which I want to tell starts with knot theory. It's devoted to study of knots and links. And a link is an embedding of a bunch of circles into a three-dimensional manifold M. All manifolds here will be, my lectures will be oriented. They may be compact or not, may have band error or not. And so this is a link of n components. And a link of one component is a knot. And classically, this M is just R3. And so links every link can be represented by a diagram. So maybe I should show some examples. This is the unknot. And then the simplest, so to speak, knot, which is non-trivial, is the trefoil. I'm still learning here. Sorry for the suboptimal drawings here. I think I would just let it go like this. Well, let's see what happens here. Oh, yeah. Okay. Hopefully this will get better soon. My abilities here will get better soon. This is trefoil. And well, there are other more complicated links. And maybe I should show you actually the simplest non-trivial two-component link. This is called Hopf link. So links were utilized in sailing, in all sorts of trades since ancient times. They appear in arts as well, like in Irish art, for example. But the mathematical of links were studied perhaps starting with van der Moot in 18th century and then Gauss in 19th century. There's a page of drawings of Gauss of knots from the age when he was 70. And so in order to represent links by their diagrams like this, we need to exclude wild knots and wild links. Gotcha.
Okay, so now I am showing you something that Adam prepared. So I share screen and voila.
That's a wild link, a wild knot in particular. You can see that it has infinitely many crossings, and here you have some accumulation point. Okay, let's go back to my talk.
So may I have a question? So you defined a link as a mapping from the sum of circles, but the sum was finite. And how about that?
That one is also a mapping of a single circle.
Single circle. Okay.
Yeah.
Okay, so it is not like an infinite disjoint union, yes?
No, these circles are going smaller and smaller, so it's still a compact space.
Okay.
Yeah.
It's not only compact, but it's connected.
Yeah, compact, connected.
Okay.
So to exclude.
Wait. I forgot to give you payment controls.
Thank you.
Okay.
So to exclude wide links, when people traditionally do two things, either work in piecewise linear topology. This is often called the PL topology, in which, well, sorry, I shouldn't need the word topology, category.
Eraser. Random.
So in this category, all three manifolds are triangulated, and links consist of lie in one skeleton of those manifolds. Or alternatively, you can take M smooth, and then you take L to be an immersion. So this cannot be, so this picture which you saw cannot be realized by an immersion because the velocity of the points at this accumulation point must be zero. All right, and so usually people do those two things. It's not a big sacrifice because Moser proved that every three-dimensional manifold has a unique piecewise linear structure. This is something which is called Hauptvermutung. It's not an easy statement and easy to prove statement. And also it was proved actually Hauptvermutung was proved by somebody else whose name escaped me now. But still, every three-dimensional manifold has a unique smooth structure, and that was by Moser.
Sorry, the same is true for four-dimensional manifolds regarding PL and smooth, yes?
No. Definitely not. There are exotic smooth structures, for example, on four-dimensional manifolds.
Yes, but I mean this part that every four-dimensional PL manifold is smooth.
Oh, this part. It's believable to me, but I'm not an expert.
I think that PL starts to differ in some higher dimension.
I see. Yeah, that's beyond my pay grade. It's a notch-trivial piece of mathematics, so I'm not sure. So we will work in those categories. As I said, there's a unique PL structure and smoothness, so there's not a big of a sacrifice here. Now I would scroll the board up, and I don't know how to do it. Should I just
Plan.
So I'll create a new board?
Yes.
Okay.
And you have only 20 boards, as we found out.
Oh,
That's your limit.
okay. And we'll recycle.
But you are going half of the speed, so it's fine. Okay. With the speed, you will use 10 boards.
All right. So, so links can be represented by their diagrams, not uniquely, obviously. And in fact, Reidemeister proved that any two diagrams which represent isotopic links, and I think I should mention what it means. It means, so we consider links up to isotopy, which means homotopy in the space of links, so in the space of embeddings of circles into M. And then the Meister proved that diagrams represent isotopic, and the full name is ambient isotopic links, if they're related by three moves. The first one is like that. The second one is, well, in fact, to be very precise, I should also consider this part. Second one is that. And the third one allows to redirect arc around the crossing. So any two diagrams which represent the same link are related by a sequence of moves like this. And although it may seem that links perhaps belong to some esoteric niche of topology, they're actually very important in topology, in three-dimensional topology. For example, for the following reason, so I'm going to talk about surgery now. So take a knot K in M, three-dimensional manifold, and then let SK be, oops, this was too sloppy. Let SK be an open tubular neighborhood. Okay, in M, and this will be closed one. And oh, okay, this is K. And so a surgery on K in M is something which is obtained by.
K is a knot, right?
Correct. It's obtained by taking the complement of the open tubular neighborhood, and removing open tubular neighborhood creates a boundary which is a torus. Take a union of it with this closed neighborhood, which is a solid torus. They're both solid tori, just open and closed. And then you can consider gluing them together through some homomorphism of a torus. Homomorphism of a torus. And if you do it right, you will get. Oops. If you do it right, you will get M back. But there's plenty of choices of torus homomorphisms, and they will give you different manifolds. And this is called the surgery on K in M. And Licorice proved that every three-dimensional manifold can be obtained on a surgery on a link in S3. Well, at least closed one can be obtained on a surgery on a link in S3. And different surgeries on different links can give the same manifold. However, here being classified this ambiguity. So Kirby defined something which is called Kirby calculus. Which describes how classifies moves between knots and links, which provide the same, which lead to the same surgery. So
I was wondering if Hilgard splitting of S3 would be a good example, because it's obtained exactly by homomorphism on the torus, two torus. But I don't see a knot inside. Just a circle, maybe, I don't know.
Well, so what you are talking about is you take a simple Hilgard splitting, which is splitting into solid tori.
Exactly.
So in fact, you're doing a surgery on the unknot, because a core of one of those is the unknot.
Okay, I'm happy. That's what I thought. Yes.
Yeah. So
You obtain S3.
Yeah.
so this,
Yes.
so
Simplest manifold.
that's right, and the simplest Hilgard splitting, because S3 has a lot of Hilgard splittings. So this method gives a very concrete construction of three-dimensional manifolds, which I thought maybe you like because it's like three manifolds which one can see. It's the spirit of this semester. But but historically, but okay, I should tell you that also. So this is why people care about knots in three-dimensional topology. But you will see soon that are also related to some deep topics in physics, algebra, and also in analysis. This is my first time I'm going to talk about knots and analysis, so it will be great. But historically, the main problem of knot theory was to classify it on knots and links. And this was done by Tate and Kirkman and Little already in the 19th century. They had tables at the end of 19th century. They had already tables of knots. And Piotr, show us the modern version of those tables.
And scroll down.
No, this was on the website.
On the website.
That's right. So yeah, so the diagrams here are listed by their crossing numbers. So number of crossings are not real topological crossings; they appear as crossings on a page. And this is as you saw trefoil. Frankly, there's another trefoil where the crossings are reversed, which is a different one. So there are two nodes with the diagram of three crossings. And as you can see, the numbers of diagrams with given crossing number are increasing quite rapidly, almost exponentially.
There a known formula for how many nodes with a given crossing are there?
Classification is done. I'm not sure. Maybe 18 would be my guess if I remember correctly.
It looks like DNA to me.
Sorry?
It looks like DNA.
Yes, in fact it is. There is
Like proteins rather.
Yeah.
biologists study the entanglement of knots, sorry, entanglement of DNA strands, and they are using some methods from topology.
DNA is unknotted, so these are proteins.
That's right. Yeah. So so there are two steps in the classification. First of all, one can generate all the diagrams. It's sort of a combinatorial problem, which is not too difficult. And then the hard part is proving that two diagrams represent different knots.
Just a stupid question. So how fast the growth is? Because for instance, when you have this famous Dedekind problem of the number of elements in a free distributed lattice on n generators, the growth is almost double exponential, 2 to n.
That's right.
What's the growth here?
I don't think it's known, but it's no more than exponential.
Okay, that's
because there's 2 to power n diagrams on n crossings.
okay. Yes.
There are some more precise. There's something called alternating knot, where under and over crossings are alternating, and then there are better bands on them. Now, Piotr, if I can ask you for the next picture, from the second picture from my PDF.
Voila.
So so now that you know knots, here's a question for you. Which knot is that?
It's a green one.
It's a green one.
You are asking, so probably this would be unknot, I guess.
Very good. You guys are fast. It's
a psychological argument.
It is
I wouldn't be asking.
That's right, and indeed it is an example of it's a non-trivial diagram of the unknot. Notice that it's really non-trivial because there is no Rademeister move which can reduce the number of crossings here. The only way to bring it to unknotted is you first to have increased number of crossings. So this shows that the Meister moves do not provide any finite algorithm for untying knots or relating to knots. All right, let's go back to my board.
All right.
So this means that this estimation is very not non-effective.
Which estimation?
This exponential one, because counting number of crossings can count many fake
Oh, yeah,
knots.
that's right. Okay. So, yeah, I only gave an upper, but obviously,
Yeah,
obvious one.
it's better in reality.
Well, in fact, it's a good question. I don't even know if we can prove that, that the growth is strictly higher than polynomial. Although I suspect that we can. All right. So,
I again forgot to give you back the controls.
so historically, people would distinguish nodes trying to use some methods of algebraic topology. You know, we can consider, for example, first homology of the knot complement. So let me just be in R3.
And this Kirby is Robian Kirby, right?
Sorry?
The name is Robian Kirby.
Correct.
Okay.
And so people would use, so this is an example of an invariant of links. So this is an algebraic quantity which is preserved, defined for every link diagram and preserved by the Meister moves. So it's a very simple one. Unfortunately, it's not very effective because it's just the free abelian group of rank being the number of components of L. Then you can consider a much stronger one when you take a fundamental group of link complement. However, there is no algorithm there's no solution for the isomorphism problem of finally represented groups. And in fact, the example which you saw of the unknot, I gave it to, I put it into input to certain computer program which deals with knots, and it gave me a presentation of that group, a fundamental group, which usually it's able to identify as a abelian group if it is a abelian group, if it is G. And in this case, it was not able to verify that whether this is Z or not. So this is not practical.
I have a question. Why cohomology?
Oh. Yeah, actually it could be both, yes. It could be also homology, whichever.
There's no torsion.
There is no torsion. How about this? We can have both. Either way, it's good. So historically, people would consider branch coverings of L3. Well, coverings of L3, branch over L, and study homology groups of those. And those kind of methods would lead to some ways of distinguishing different things.
Sorry, could you say a few words about this notion of branch covering? So, how to think about it?
Yeah. Well, okay. Imagine map from C to C, sending Z to Z to the power n. Branch covering of C. Now, a branch covering of a three-dimensional manifold. Outside of branching points, it's just a regular covering. And on branching points form one-dimensional manifolds. And locally, they look like this map cross I. So now multiplied by R. So C cross R, C cross R. Yeah, so locally, okay.
Okay, so C is two-dimensional, therefore the branching is one-dimensional. It is always one of codimension one, or?
It's codimension 2, branching is one-dimensional, as you said.
Yes, but in general, if I have something which is n-dimensional,
then branching would be codimension 2.
dimension 2.
So then, well, in our case, we only study three-dimensional manifolds, but in general, you could put Rn here. And yeah, well, I imagine you could define some class of branch coverings where the branching is lower dimension, you can generalize this concept. So, but it will not really, I just mentioned this in passing, will not really need it. I want to tell you.
Sorry, this codimension too is related to the fact that we somehow think of it in terms of complex numbers and yes.
No, the complex structure was just to make my life easy. It means that we have three-dimensional space, which is covering except for spaces of branch points, which are links. Around the branch point, the covering, well, it's just multiple covering of what the space which you have around, but there is a singularity given by at the dimensional.
Okay. But if you cut the singularity out, I mean, think of a very specific case that you're just on the circle, not on a complex plane. And you think about this S1 to RP1 non-trivial vibration. So at the level of C-star algebras, the way you would go, it would be exactly by squaring the variable.
Oh, nice.
That's exactly the embedding of C of RP1, C-star algebra, which is again circle algebra. You embed it in C of S1. So you have a proper inclusion of C of S1 in C of S1. Why? Because you square the generator. So it has some nice topological meaning. You can see that there's a double cover. Of course, you can have nth cover if you want.
Okay, thank you.
But you are considering only finite branch coverings. So logarithm is excluded.
Correct. Sorry.
Logarithm, the Riemann surface of the logarithm is excluded.
Well, it was really a side comment. I mean, you can also consider unbranched infinite cover. And in fact, they are considered. You can consider infinite maximum abelian cover of not complement. And by studying homology of it, you can define an invariant, which is called the Alexander polynomial. Now, I want to tell my story and to talk about John's polynomial. We need to use braids. So an n braid n braid is an embedding beta of n circles, sorry, this time n intervals into a cube, which I will denote by I. So I will denote by Q. I is just the interval 0, 1. And in such a way that the zero ends, it has n zero ends. Those each interval has the zero end, and they all go to let's do it this way. 1/2. So we're in the middle.
I'm confused about the union. Is that this joint union?
This joint union. 0. And then, you know what, maybe I feel like maybe I'm overcomplicating it and I should just show a picture of this. And I will. And then one ends go the same, except there is one here. And then level T points, let me just write it like this. Level T points go to T here. Okay. An example of a 3 braids. And braids are considered up to isotopy, like links. And isotope, again, is a homotopy within the space of braids. So for example, this one is related, is isotopic to one like this. If I didn't make a mistake.
So this first coordinate, which is 1/2, is perpendicular to this whiteboard, yes?
Correct, yes. Yes, this is, so maybe that's not the standard coordinate axis. The first one is perpendicular. This is t equals 0. I don't know what happened here.
It should stay away from the edge of the board.
Yes, I'm learning it hard way. And now what do? Oh, thank you.
And just don't go too close to the left.
Need to. So this is t equals 0. This is t equal 1. Okay, and so for example, not a braid. And because at level t, they have to those embedding have to be monotonic with the t variable. And as you will see in a moment, braids are very important for topology and for knot theory in particular. Let Bn be their set. So this is n braids. And this forms a group. And the reason for that is, well, you just group under stacking. You have another braid on 3 strands. So then you can just compose them and they form a group. And maybe the fact that composition is invertible is harder, but you could draw here the first crossing the opposite way to undo this one, and then continue with crossing here and crossing here, and you will get the trigger braid, which is the identity in the group. Right? And so this braid group is generated by elementary crossings, sigma 1 to sigma n minus 1. So 1 I plus 1 n. This is sigma I. And then it's subject to relations. Sigma I, sigma j, they commute with each other when I and j are at least 2 apart. I think that's straightforward. Yes, so I plus 2, so this crossing and the crossing starting with I plus 2, between I plus 2 and I plus 3 will be unrelated to each other. They commute with each other. And then there's this extra relation which says sigma I plus minus 1. So one can prove the fact that these are the generators is straightforward. because every braid can be composed of crossings, elementary crossings. But the fact that this is a complete presentation perhaps is less trivial. Maybe I should mention that if we did not insist that these are embeddings, and then we would be allowed to change crossings. And what kind of group would we get then? We allow change crossing changes. Well, then sigma square would be identity in particular. And anybody can guess what kind of group would we get if we do that?
Permutation?
That's right, that's right. So we will get homomorphism of this group onto the permutation group. Yes, so B1 is just trivial group, B2 is Z, just can have one crossing repeated many times. And then B3 and higher, and for higher n groups are already non-commutative because they project non-commutative permutation groups.
I have a question, but not to you. I don't know, Magnus is online, yes, and Tomek, because the quantum group question. You know, we have a beautiful version of quantum permutation group, like a free quantum permutation group. I was wondering, can we have the same type of a free quantum totally non-commutative braid group?
I'm all ears. But I don't know.
I don't know. Magnus, if you know anything, just weigh in. Tomek,
It was not studied.
it was not studied, just occurred to me, yeah. Because you see, you can very easily write down permutation in terms of matrices. Once you are in terms of matrices, you can express everything in terms of C-star algebras. Now, the only thing that you say that, now the entries in these matrices do not commute. They satisfy all these projection properties, you know, rows and columns and up to one. These are all projections, but nobody tells you that they are one, right? They can be just.
The problem is that the linear representations of this group is not as easy as for permutations.
Yeah.
Okay.
There are more presentations.
Especially faithful representations.
Okay.
Yeah, so as in the case of diagrams, link diagrams, well, before I actually go there. So once you have a braid, you can close it to obtain a link, and new board.
Yeah.
Or yeah, well,
We have 20.
so you can have a braid beta. I'm going to be lazy here, like this, and then you can close it, which in this case means you're going to connect the ends like this, and then you obtain a link. And as in case of link diagrams, well, first of all, that's a good news, yes, because this means they can represent every. Okay, well, sorry, guys. First of all, I need to tell you the theorem of Markov, actually of Alexander. Alexander proved that every link diagram can be presented in this way. So every link is represented by a closure of some braid. However, as in the case of diagrams, this is not unique. Nonetheless, it's a I think very useful fact because it allows for a very algebraic description of links by elements of some group, of some nice group. And then, as I already mentioned, unfortunately, this presentation is not unique. And so there's a theorem of Markov, which classifies this non-uniqueness. So he proved, he was a Soviet mathematician who proved in the 1930s that two closures like that represent the same link. If here. If they are related by, well, maybe I should say, if beta and beta prime are related by two moves. First of all, conjugation.
I mean, by application of two moves, that you can iterate it, right?
By a sequence of two moves.
Okay.
One is conjugation, which sends beta to alpha, beta, alpha inverse, and two by stabilization, which sends beta in Bn to beta sigma n, which is no longer in Bn, which is in Bn plus 1. So the fact that these moves preserve the type of the link, I think is straightforward. You know, if I add here extra crossing, and this will be a positive crossing like this here, and a negative crossing like here, and then I do the closure, then of course, it doesn't matter. I can undo this crossing and this crossing by sliding one of them around. And then the second move is also not that mysterious or surprising, perhaps. The second move says that I can add extra crossing here and now do the closure. No.
Okay.
I have to. This is the proper weight. So this is beta sigma n. And now I do the closure. But you see here, so this here, this goes like this. This is terrible. My drawing is terrible here, but now you can see that this loop can be totally undone. Make sense?
I understand the second move. Could you tell me again the first move? One.
Yes.
Second one is clear.
So, okay.
So alpha is a generator, so it's enough to consider one crossing.
I will repeat the drawing.
Mhm.
Top and top.
This is the original braid. And now I'm going to add extra crossing. So I'm going to put this crossing here. This is sigma. All right, you know what? I really should do a better job here. Let's do it properly. This was my braid, and now you can close it. But I can now add a crossing here.
Okay, so the difference is that now two legs of your added crossing stand on the top of
The
the
composition with the generator of the Artin group
So I'm adding this crossing here. This is sigma 2
and anything.
and sigma 2 inverse.
Okay,
It can be any braid, but this is a simple example. And now I'm closing it.
that's why it's conjugation because it's the inverse. Okay. Yeah, I've got it. Yeah, thank you so much.
Now,
This is a beautiful picture. Yeah.
and then the braid can be.
Yeah.
So basically you have alpha here, you have alpha inverse here, and you can slide alpha inverse and to alpha, and then they will cancel. So this is Markov theorem. These are called Markov moves. So this gives an idea for a link invariant. If you can associate some quantity to braids, which is preserved under conjugation, like what? Well, for example, you can consider a representation of the braid group and then take trace. And then if you can only handle this second move, stabilization, then you will be then you have a link invariant. You know, again, this doesn't give really an algorithm for distinguishing different links because unfortunately, even two links given by n braids, those braids don't have to be conjugate, they have to be stabilized, and we don't know how many times. Often more than once.
Is this Markov's theorem if and only if, or just one-way implication?
If and only.
If.
One side
If.
is obvious because clearly these moves don't change the type of a link. The other is less obvious.
Okay.
All right, so now we are ready for the Gauss polynomial, which was introduced in 1984. And he proved the following statement. So there exists a certain polynomial invariant of links, of oriented links. Going to a ring of Laurent polynomials, which is a bit unusual because it involves half integer power of t. But this is just a matter of convention. You can think of it as just a variable, formal variable. And okay, so this is invariant of oriented links. I didn't talk about them, but you can consider embeddings of oriented circles, and then you have oriented links. And such that, so to save space and writing, this means such that for me, we have the following identity. Okay, this is a shortcut for the following. Imagine you have three links in space that were given by diagrams which are identical except for one spot. And in this one spot, one looks like this. This is called positive crossing, often denoted by D+. This is a negative crossing, and this is a smoothing like that. So if you have three links like that, then he claims that there's an invariant which would satisfy this identity. And the second property is much simpler. It just says that for the unknot.
So actually, it's about V. It's a function of an oriented link, And what is depicted here, these are local crossings.
Yeah,
So this means that the rest is unchanged.
correct. That's what I was trying to explain, and
Explanation for one local modification
that's right.
oriented link.
But if V is defined on oriented links, it's a bit uncomfortable, but now we apply it to something where it is not a link.
Oh, and what do you mean? They're all links?
No, it is a link. It's a local
Yes,
fiction of a
Crossing,
crossing.
but single crossing is a link.
well, that's
No.
what I said, and that's what Tomek was saying. You can complete it to any link you like,
Uh-huh.
to the same completion of this crossing and the same completion of this one. Because all of them take place in one
All right.
for endpoints.
Okay, so okay, so you take the same completion of each of these crossings to any link, and then it's true. Okay, yeah, thank you for clarification.
And something like this is called a skein relation. Or the polynomial. And and I should say unique. I think I said it. In fact, there's only one such polynomial. And so in fact, the uniqueness is not particularly difficult.
Could you say, please, how this polynomial came out from the study of algebras?
I'm going to tell you that.
Okay.
What this story is about.
So let's compute something. Let's take an example of the trefoil. This is a trefoil. I'm going to orient it. This is a positive crossing. So this is called positive crossing. In a diagram, negative and zeros moving. And now, what if I change crossing and make it negative? So if I make it negative, I will sorry, guys. Oh, I guess I do have a local eraser for this. Let me try it again.
Maybe it would be better to start from the crossings.
Yeah, you will have something like this. Now, on one hand, so now this is negative. And then on the other hand, I also need to consider smoothing of it. And the smoothing will be like this.
Sorry, is it also the second one really the negative or the first? I think that the left part of this is the same. Sorry, the left
So
part is different, but the right.
There's a local change.
Local. Okay.
Yeah, only change this crossing.
Yeah.
Now this is a pretty bad picture, but here there's a smoothing. Maybe the. Do you see it, that there was a crossing here and now there is a smoothing here? Now, this is the unknown.
In this orientation, it's not so easy to see. Maybe you should change the orientation.
Okay, yeah. Although it's pain now to do it.
Because if you change the orientation, then precisely your choice of plus and minus would be as is
I agree.
in this relation.
I agree. Just if I do the eraser, okay. If I do eraser, I don't want to erase everything, and
No. So you will erase only this arrow.
All right, customer is always right.
On the arrowhead.
Sorry.
touch only arrowheads without touching.
Oh, I see.
Erases.
Okay,
Connect.
good point. Good point. Why?
Yes.
think that maybe connected component, but counting as a history of visitor if it was drawn in.
Yeah, sure. So not connected component.
Right. So I will do this. Oh,
Right. Historically, yes.
Yes.
by Friday, I'm sure will be.
Okay.
It's also.
Yes.
Right.
Yes.
And I didn't draw anything, which was good. So this is already the unknot, as you can see. This is not, but then you can, and somehow I missed that my arrow here. But now we can again do this trick on either crossing. Yes, so I can. I don't want to waste too much of your time, but if I do this operation to this crossing, then I get trivial links in either case. Well, if I change crossing, obviously this loop will be unlooped. And if I smooth it, I will also get I hope you guys trust me on that. So something like this is called a skein tree. And so this will be, well, actually, if I'm going to do it very quickly, I'm just going to.
I'm confused with this smoothing picture.
Yes.
How do you see that this is just a circle?
This
This is no problem. This I have no problem with.
Yes.
How about the second one?
Do you agree with,
There are two circles.
do you agree with this picture?
Yeah, but I
Finally, if you smooth both,
Okay, well, we can just do it.
because right now it's two circles. Okay, so you have to do one more move.
So, yeah, so I will have this. I will have this.
Oh, yes, because the relation you have this minus the opposite. Okay.
There we have. Move. As you can see, I can talk about knots, but drawing knots.
Undo.
Oh, this is in course, yes. Okay. All right. So if you smooth it, you will get an unknot. Do you see that? And I could try. Oh, actually, I know how to smooth it. Yes, so the smoothing should be like this. I believe that's sort of a artistic rendition of what happens after this movie. So it's under the unknot. Okay, this is called a skein tree. We know the value. Oh, well, maybe we don't yet, but there's a lemma. We can compute the value of the unlink from this relation. How do you do that? Well, we have this relation now.
and around the crossing, the orientation is downwards.
Yes.
You're missing V after T.
Oh, yes. So we have this relation. This is unknot. This is one. This is one. So out of this relation, we get the value for the trivial link.
They're telling us that V of infinity minus V of infinity is V0.
Yes. With some coefficients.
Yeah,
So
Oriented infinity.
oriented infinity.
in fact, this is the I'm going to tell you what it is.
Sum of squares.
Going to be the sum of those two powers of k. After you do the division arithmetic here involved. So in any case, we can compute the value of the unlinks in this way to trick. You can, for the treble, we created a skein tree. All the leaves are the unlinks. And therefore, by using this relation, we can compute the value for the treble. Does this make sense? And there's a theorem. It's not a difficult theorem to prove that any diagram will have a skein tree like that. So you can always compute the Jones formula.
Sorry, so what's the idea of a skein tree? You have your link, right?
Yes.
In your link, you choose say one crossing, D plus.
Yes.
D plus.
In fact, you have a diagram of a link
Correct. It's better to talk
Okay.
about diagram.
We have a diagram.
with crossings.
Fine, yes. And you randomly choose one crossing?
No, you do it smartly, and I can tell you how to do it. I was just trying to make it simpler to you and say there's always a way to choose crossings so that when you change the crossing and resolve it.
Okay, so not random.
Another one.
You smartly choose a positive crossing,
That's right.
a link, and then next step.
Well, you consider its negation and smoothing.
Okay,
Now-
you have two modes, yes.
Now it's enough to compute Jones for these two. Because this one will be determined by this identity.
You are right.
And then I can recursively choose smartly crossing. And it's like this one, it's negation and smoothing. And then instead of computing Jones for that, I will just compute Jones for these two. And I claim I can iterate this process so that I reduce all the calculations to the unlinks, like unnot,
Yeah.
unlink, and the un.
Okay, got you. Yes, thank you.
Great. So the uniqueness is really simple. The existence is much harder. It's a much harder business to prove. And but I'm going to talk about this. I'm going to prove the existence of that. But I should tell you that what really surprised topologists and the whole math community was not really maybe the existence of this invariant, but also the inspiration of Jones, who the work in von Neumann algebras, which led to definition of this invariant. And this work led to a revolution in knot theory. In 1989, Witten defined Jones in the context of Chern-Simons field theory. And he also defined invariants of three-dimensional manifolds, not just knots and lengths. However, his work was on what we call a physical level of rigor. And then in 1 year, actually in 1988, so this almost the same time, unrelated to that, well, Greenfield defined quantum groups, were also considered by Jimbo a few years earlier. And then in 1989, Reshetkin and Turayev used the representation theory of quantum groups to define something which is called quantum invariant links. I don't know if I should try those things.
Could you maybe say a few words about the main motivation, original motivation of Greenfield and Jimbo? Since I'm more familiar with this approach by Voronovich, and for this approach in the quantum group theory, the motivation, at least for me, is very clear. But I never somehow understood how Jimbo and Greenfield were originally motivated.
I forgot how, I never read papers of Jimbo, and I forgot what was the motivation of Greenfield. Well, he was considering the formations of, Greenfield was considering, was interested in something which is called Young-Baxter equation and scattering theory. and he introduced quantum groups in that context. And actually, I'm going to come back, if we have time, we're going to come back to quantum groups and to talk with them. Yes, for now, I just want to maybe say then, well, just say, so Witten, so breakthroughs, Witten, 1989, Chern-Simons, quantum field theory.
So you are mentioning a sponsor.
Yeah.
That's right. That's right. Yeah, yeah.
How proper of you.
Yeah. In fact, yes, most of what I'm going to talk later on Wednesday, Friday will be inspired by his work. And then, but this was not really what we would consider rigorous, sufficiently rigorous for mathematicians, perhaps. But then Reshitkin and Turayev, I'm just going to write RT, defined quantum invariance of links. Which include the Jones polynomial, but are more general, which I plan to talk about, which are based on the representation theory of quantum groups. Now, in a moment, I will tell you about the work of Jones on polynomial algebras, which led to this discovery. But let me say a few more things here about this. So first of all, this revolution started in 1990s, let's say, but it continued. It actually continues until today. Now those discoveries connected knot theory, Jones polynomial, to other sophisticated areas of representation theory, algebra, quantum physics, and also are subject of investigation, and particular properties of the Jones polynomial are still kind of quite mysterious. As an example of that, I should provide you, I can state a conjecture of Jones, which is called Jones unknotting conjecture. Maybe I should write it.
Sorry, this non-rigorous part of Witten's results were related to the fact that it has to do something with quantum field theory when you take functional integrals, yes? And this is something which is not mathematically well defined. Yes?
Particularly, yes, the use of path integrals there. So Jones and not conjecture says that if the Jones polynomial of a knot is 1, then K is the unknot. Jones polynomial distinguishes the unknot. So even the simple question is still open. However, I have a theorem with my student, Obtuzum, which says that it's true for diagrams with at most 24 crossings. So this was done through huge computational effort using supercomputer.
Classical computer. Classical computer, not quantum.
Yes, we don't have those yet at UB. That's one comment. So yeah, the properties of Jones polynomial are still mysterious for knot theorists. The second comment which I want to make is that soon later, after Jones discovered his polynomial, people in this acronym, hopefully, so maybe I should make it a theorem, generalized it to a two-variable polynomial of links. And so they proved that, maybe I will just use a shortcut, there exists invariant of links, which we can denote by capital H. And it's in, Laurent polynomials now in two variables. I'm going to use maybe non-standard definition of it, such that X of a diagram with positive crossing plus Y of H negative crossing is just H of the smoothing. And then H of the unlocked is 1. Okay, the name of the polynomial is Confline, and with PT silent, this is an acronym. First, when I was learning not fear, I thought it was some very smart guy. He said it was Confline, but that's not the case. This is acronym for the inventors, for people who discovered it. Hoste, Okneanu, Millet, Floyd, Licorice, Jeter, Przytycki, Traczek.
Wow.
Przytycki, Traczek did it independently from here. They were in Warsaw at the time. And well, you can imagine, so those coefficients which you saw there are not really special. Again, the theorem is very non-trivial. It's not obvious that such a polynomial must exist. Polynomial invariant must exist, but the uniqueness is fairly easy. And you could of course imagine also putting a z here if you like, but that wouldn't give you much because you can divide both sides by z and it's both to two variables.
Does it relate somehow to John's?
Sorry?
Does it relate somehow to John's?
Yes. So a special
algebraic.
So if you put T inverse here, T here, T 1/2 minus T to minus 1/2 here, and then you divide it, then you get to this form. If you divide both sides by what you see there in the John's polynomial.
I don't remember John's, okay.
All right.
Go back. X equal.
I will do it.
X equals
Was T inverse T. T the 1/2 minus T minus 1/2.
And divide.
Now,
And with the plus on the left-hand side, yes? Or those with the minus, yes?
it's minus here.
Yeah.
And now, so you have this coefficient, divide both sides by this coefficient. Then you have exactly the same left. Here you have T inverse divided by that.
Okay, I've got you. I've got you. Yeah.
By the way, going back to the John's anode conjecture, you can ask, what about links? Is it true that the John's, if John's of L is the John's of unlinked n components, then L is unlinked? And the answer is no. There are examples when this doesn't hold for more than one component.
I have a stupid question. This ring on the right-hand side.
Ring on the right-hand side, this one.
T of, yes, x plus minus 1 and so on. So this is the group ring of.
Yeah, Sikora.
Yeah. So does this have some?
I'm not sure if this makes this really has some deep meaning here, though. Well, it's a kind of obvious algebraic fact, yes. But well, I don't know. I don't know where you are going with this. Maybe I'll be happy to talk about this. All right. Well, so this much comments from me about the Jones polynomial, and now let me try to explain how it came to be through in work of Jones on polynomial algebras. So okay, now change of notation. I started writing M, so I apologize. So now M is not going to be a free manifold, it's going to be a 2-1 factor. Okay, what's a 2-1? What's a factor? Factor is a fundamental algebra. What's that? Well, that's an algebra of bounded operators on a Hilbert space, which is closed in some topology, operator topology, I guess. And what is a factor? Well, it's a fundamental algebra with trivial center, which means center is being just C, and with trace. So it has a trace tau, which is which is a state, a positive state, which is faithful, and also I should say that this algebra cannot have minimal projections. I don't think I know this will really matter for what I'm going to say, but that's a quick definition of a factor, of a 2-1 factor, in fact.
Okay, and of course the tracial properties of this trace.
Yes, it has to have spatial properties. The trace has to have spatial properties. And now Jones consider the Gelfand-Naimak-Seagal construction. So first of all, there is a pairing on M, just given by the trace tau of y star x, which is positive definite.
This goes from M to R, tensor M.
Why this strange flip? What would be wrong with X star Y?
No, it doesn't matter, it's a trace.
Doesn't matter, yes.
It's a trade. Well, but the star is different. I would star X.
Yes, but you would like to have a sesquilinear form.
Yeah.
So
So-
one variable should
Well,
be
it's just-
linear.
So it's a well-known story.
Between physicists and
prefer combinations like X star X. In mathematics, we prefer X star.
this time there's mathematics approach.
Yes. If you apply trace property to this, you obtain mathematical convention.
Consider it's a completion of M with respect to this form, this pairing. And then, well, M acts on it. By multiplication. And now let's consider a subfactor. So a subalgebra a subalgebra, another factor, which is a subalgebra of M. And then this defines the completion now as above. We can do this the same completion, and it will be a subspace of L2 of M. And there will be a projection from the larger space to a smaller space. So there's a projection which I denote by E1.
First subfactor means that everything is represented on a one Hilbert space, the same Hilbert space, yes, M and N. Originally, they act on the same Hilbert space, yes?
When you say the same Hilbert space, what do you mean?
For Neumann algebra is not abstract, it's always represented on some H, yes?
Yes.
And then N acts in the same space H.
But
I'm not saying about GNS construction.
But it's not true that it's not always abstract.
But
It is concretely represented.
Yeah, but it also has a definition without being.
This embedding place.
Yes, but if we are saying that we have a subfactor, we mean not something which isomorphically embeds in M.
Sure. Yeah, this is.
But everything
Yes.
it's an algebra of B of H with the same H.
But
That's
why?
what I mean.
Why?
I don't know.
It's just a algebra.
It's a factor.
How he did.
Nothing wrong.
I'm not sure if this is an essential.
Hilbert,
Yes.
Hilbert space arising here is this GNS construction.
Okay. But we don't care, yes, about this
So now
spatial structure, original spatial structure.
M1, which will be larger than M, which will be actually generated by M and E1.
Or E1.
No, sorry. Generated by N and E1.
That's E1.
So it will be subalgebra of well, yes, it will be a subalgebra.
I'm confused about this E1. Is it a map from L2M tau into L2N tau, or is it a map from L2M tau into L2M tau, whose
With
image
the
is L squared?
Probably the second, the latter option.
I'm not sure what you mean. It's a projection. This is a subspace of this one. So
Yeah, projection is a self map of L2M tau, whose image is L2N tau.
yeah.
That's what he means, yes.
Well, okay. So you say that I could put it. I could say this.
Okay.
So let's now M1. So M1 is going to be defined as generated by M and by N and E1. So this will be, so where is M1? Will be in L2 of M, generated by N and E1, which act.
Sorry, now I'm confused.
No.
L2 is a Hilbert space, yes?
Yeah, it's not here. It's an algebra of operators. So let's act.
B
Let
of L2, maybe.
yes.
Maybe.
That's right, that belongs to B of L2M tau.
So M1 is algebra of bounded operators here, which is generated by N and E1. And so now there is a theorem, what Jones proved, it's a theorem, which says, in fact, I should say this is called Jones's basic construction. Okay, so
Jones tower, right?
and so I should state the theorem here. Jones proved that if the index of N in M is finite,
Is it the Wapapani index?
it's a subfactor index, and frankly, it's a more complicated story, which I don't think will go there. It's a dimension of Frankly, I don't know all the details here. I think it's a complicated story of what this index is. It's a real number. It's some sort of dimension of this space over n, but dimension in a funny way. If this is finite, then first of all, n is also a 2-1 factor, and also m1 is a 2-1 factor. And the index of m in m1 is the same as this index. Right? So I will not write it, but I will just repeat that this is called Jones's standard construction.
Sorry, I have a couple of questions. And you are writing this. I try to squeeze myself in 2 questions. First thing is that if we write this index on the first half, we have a bigger von Neumann algebra, yes, on the second, a smaller one.
So we are somewhere here.
No. If we write this in the index, yes, first one is the bigger, the
Yes.
one is the smaller.
Correct.
Okay. Second question is the
Why
following:
only one?
if we have a subfactor of something which is 2-1 factor, it is not necessarily a 2-1 factor automatically, yes?
But if it is finite index, it should be automatically
If it is
non-trivial way to 1 factor.
if it is finite index, but without this assumption, it is not necessarily true. Okay, I promised a couple of questions, so let me ask the third question. Could you give some examples, for example, for free group von Neumann algebra and also for the hyperfinite? What are those indices? For example, if I take a free group with 3 generators and free group with 2 generators, what is the?
Is it a factor?
Yes, it is infinite conjugacy class, and in this case, you get factor.
I don't know if it will be finite index.
Oh.
Maybe it was. I don't know if I could do much for you because I don't know if there's some elementary description of M1 other than what you see here. So I don't know if there's some enlightening example of this.
Sorry, could you explain to me why M is embedded in M1?
Well, because M acts by banded operators on L2M.
So
And
this means that M1
Must already belong to
it is generated by N and E1.
Well, maybe it's actually generated
Yeah,
by
so something strange here.
By the way, in the meantime, let me answer my own question. So go ahead. So Watatani index is a sister version of the Jones index. And when you are talking sister algebras, you have some nice formulas.
Mhm.
Okay, so I was right. It's just
Is there an analog of Jones polynomial for sister algebras?
I'm not saying this. I'm just saying extension of Jones index to sister algebra was argued by Y. Watatani in terms of quasi basis. In this paper, we adopt his definition of index.
Mhm.
Okay.
Tomek, you are of course right. Yes, must be.
Okay, now it's okay.
So again, basic construction, and now Jones repeats this construction. So because if you start with finite index, you get, so you have n inside of M. Now you have M inside of M1. It's also finite index. The 2-1 factors, and
Yeah, I'm sorry, but it's so funny because when I typed Jones index, it showed me Dow Jones Industrial Index.
Yeah.
So this bad name.
it's a good angle to apply for brands.
So idea is that adding this E1, this is something which no longer belongs to M, but still it is somehow not completely out of M since this index is the same, yes? So.
Yeah.
Huh.
So yes, so I hope you guys can kind of remember what's happening here, but this is the first step of building a tower.
Yeah.
It starts with n inside of M, and then you have M1 over it, and then you have M2 over it, and so on. So this is Jones's tower. M1, M2, and so on. And each of them contains those projections. So you have infinite number of projections. And then Jones studied those projections, and he proved that they satisfy certain properties. So this is just star does not change it. They are projections, so that's obvious. And then EI plus 1, EI is the same as T over 1 plus T square for certain T, EI, for certain complex number T, and for EI and EJ commute as long as I and J are not adjacent. As long as they're not adjacent.
Sorry.
Why not to write it? It's greater or equal to 2.
It was written in this form before.
Wait, Alan. When I read here about the basic construction of Jones, it assumes that these are finite dimensional phenomenon algebras. No, sorry. I was saying straight. Both are finite. What does it mean that phenomenon algebra is finite?
It's finite dimensional, but these ones are not. But I'm going to get to finite dimensional ones now.
No, but finite mean that finite in the sense of this Murray von Neumann ordering of projections. That if two projections are equivalent in the, there is no projection which is equivalent to its proper sub-projection. This means
okay, that's
like finiteness.
Yeah, thank you so much. Yeah, thank you so much. Yes.
I don't think the M was finite. So
no, it is finite. Every 2-1 factor is finite as a finite Neumann algebra in this sense. But
in this sense, yeah.
Yes.
Because when you say finite algebra,
mean finite dimensional.
Exactly, because this will be finite. Now we are going to talk about finite dimensional algebras. So the projectors satisfy those properties, and Wenzel proved that for certain T, and Wenzel proved that this can happen only when T is either positive real number or a root of unity. For K, at least 3. And then
this T is fixed once we fix the pair consisting of M and N, yes? Or is it that every time we get the same T?
Yeah. So you have to fix N, yes. So for
and this maybe you think that T is independent of I.
Yes, T is independent of I, but not from M and N. Yes, probably.
I think they may be independent of N. So yes, so we have to fix N, and then there exists a von Neumann algebra which contains those projections under this condition. And then Jones proved that in fact there is a unique one. Finite dimensional algebra, AN, containing those projections with trace. And satisfy the following conditions. So this is 4, 5. The trace is, let's normalize so that the trace of 1 is 1. And then trace of RB must be BA, trace of BA. And then trace of any element. So this one is contains, yeah. Well, okay, so this is equal to certain scalar. Actually, the one which you saw there, times trace of W. And then the last condition is that it's positive. So trace of A star A is greater than 0, actually positive and faithful for A non-zero.
So sorry, so AN contains those projections E1, E2 up to EN, yes, not all of them. As you mentioned that these AN are finite dimensional, yes.
So, okay, so it comes, AN comes with trace N.
AN to C, yes.
And N plus 1 trace N, yeah.
And also trace N goes from AN to C, yes.
N next to A.
AN.
Did this clarify that?
No, AN.
Trace N.
AN, yes.
AN.
Thank you. Yes, right. And so E1, En belong to this algebra.
Okay.
And so Jones proved that there's actually unique von Neumann algebra with trace satisfying all those properties.
And what is T here?
T is a certain complex value. So when you start building this tower, you will have those projectors.
Equal to I. Complex values.
Yeah, you can get up. So depending what you choose for M and N, you may get T equal to I.
But then I would have 0 in the denominator.
For K equal to 4, it's
I see.
K equal to 4.
So here that's better.
It's
No, so I is not possible. Yes.
no. For K,
You misunderstood.
4.
Tomek, wait. You misunderstood my question. If T you wrote is real and you just said it's complex, okay. So
No, I didn't say that's real. It's an or.
I'm sorry.
So for K equals 4, you obtain I.
Okay.
Plus minus.
Okay.
And you have a
Yes,
And I have a problem. So I was right. Yes.
you guys are a tough crowd. I don't know. Good point. So should it be? So this is suspect. Maybe so should be also excluded. I don't know.
It's an alternative, but nobody says that it must realize.
I took
Both cases must realize for all K.
the paper of Jones, and there is some, as you pointed out, some issue here. So maybe it should be more than. So this will be for K equal 4. Yes. So maybe we need more than. Not that it will matter in any substantial way, but
If you choose the first, the primitive root, you don't have this problem, yes? So not 2 pi I, but 2 pi over K, and K greater or equal than 3. Then it is fine.
well, no, you don't
You
need.
have to have I because it's understood.
Yeah, we need I.
It's a complex.
Okay,
The root of
okay.
primitive.
Sorry, forget it.
Yeah, there's some typo in John's paper. Yeah, luckily not really essential for our story. So then it turns out that these algebras, not in the context of von Neumann algebras, but just
Confused.
algebras in normal sense of non-commutative algebras. These two preconditions define they define something which is called temporary leap algebra.
Not temporally leap Jones algebra.
Temporary leap.
Temporary leap algebra. I guess sometimes it's called Jones, although they were earlier, and they did consider these algebras in context of Potts model in statistical mechanics.
Percolation. Theory of percolation.
Yeah, so Potts model is about it considers a crystal with some electrons, I guess, trapped in this crystal, and their spins models the behavior of spins of those electrons. And yeah, and okay, so now what has to do with knot theory? Well, those relations are kind of related to relations in the braid group. And the trace actually turns out to be very useful for what we need to construct a link invariant. Okay.
7 looks like stabilization.
To notice, but it's easy to prove that, first of all, you can send sigma I, the elementary crossing in braid, to GI, which is going to be square root of T EI. Maybe this is not the optimal way to write it, but why not? For I equal 1 to n minus 1. This actually defines a homomorphism. A group homomorphism. And that's noted by Rn.
By group.
Well, because Bn is a group, and it will go, I know this is weird, this is an algebra, but it will go to invertible elements in An. So it will define a group homomorphism. And then second,
Why GI is invertible?
not obvious.
Oh.
Yeah, but if you like it better, I could. Well, how to prove it? Well, basically, you just take in. Yeah, I didn't specify what the inverse is. Well, the good news is that the algebra which we saw looks complicated. I'm going to give you a simpler model of this algebra later on.
So this leads to some relation between these projections, because then if you take sigma I inverse, it must go to G I inverse.
Correct. Yes.
But yeah.
It's not obvious.
What could be the inverse of?
In the model, I don't want to spend too much time perhaps on this, because I will give you a simpler model of temporary leap algebra where those things will be much easier to see.
Okay.
So second of all,
In terms of temporary leap diagrams?
no, in terms of tangles.
Tangles.
But maybe you should finish the sentence. Defines.
Well, group homomorphism.
Yeah, but you should write group homomorphism.
And second of all, you can define.
You can take the group algebra and then it will be algebra.
If you prefer,
CBN.
If you prefer, we can do this.
CBN, yes.
I don't know. Yeah.
Yeah.
CBN to AN.
It's an algebra.
It's an algebra.
Very good.
Yeah.
Customer is always right. Let's define now better. There's some normalization factor. And it will be just as you can expect, trace of Rn of beta. And so I claim, well, Jones observed that this is preserved by Markov moves. Observe
So by 6 and 7.
Oh, good memory, yes. So the Markov modes of course were 1 and 2. One of them was saying that we should be allowed to conjugate beta, but of course the trace will preserve that. And then we have the stabilization move when you add extra sigma n, and then as Tomek said, you know, this is the amazing property which makes it work. So if you see this factor, which we need to normalize, so once you observe this, actually the proof of this part is very easy. And this is well, so consequently, you know, so maybe comment or proposition. So maybe I should say this, I should now take a closure of that, which by definition is going to be that. Satisfies Jones scale relation. And once you have it, the proof is not too difficult of that. And so by uniqueness of the Johnson's polynomial, this must be the Jones polynomial.
Wait, and this definition makes sense because of the above, right? Because if you choose different beta, it's the same V of beta. Right?
Yes. And this is the Jones polynomial.
So the notation V is justified, yes.
It's V like the first name of Volkan from
That's right. Von. Yes. Maybe it should be called the Von polynomial. All right. Any questions about that? So we'll talk more about the temporary algebra, and we'll give a simple definition of that algebra. You know, this construction shows that somehow this, to me, the von Neumann algebra story was an accidental route for this construction. You can do this story without involving von Neumann algebras. But it's interesting. I don't think this was explored. In depth, maybe there is more than meets the eye in terms of von Neumann algebras involvement in this definition. So, if you are happy with this, I'm going to give you now a more elementary definition of the Jones polynomial. Can I move on?
yeah.
So 2 years after Jones, Kaufman introduced an elementary definition of the Jones polynomial, and for that he considered framed links. So this is work of Kaufman. Framed link.
In this double F of Kaufman, we have an overcrossing or undercrossing?
Oh, I don't know.
But what crossing you have in F?
I was even more complicated, yeah. So what's a framed link? Well, it's an embedding of annuli. If you remember, I was an interval embedding into M. Okay. So if you restrict it to this, I'm too impatient for the board. Restrict.
Maybe it would be better to call it ribbon.
Well, but it's a
Yes.
circle.
Because S1 is one-dimensional, I is one-dimensional, and everything is three-dimensional manifold. So
Like some people call them.
it's not like a tubular neighborhood, for instance.
Well, but it sort of defines a frame in the tubular neighborhood. Restricted to, if you restrict this to the zero part, you get a link, yes?
Yeah.
Right. It's a link with a vector field. With a transverse vector field given by those I bundles structure. I'm being slightly loose here, of course, but and which is called framing. So the point of this is that frame links are not to be. One should not be afraid of frame links. Basically, there are links with some transverse vector field. Transverse vector fields on a node are classified by just an integer. Yes.
Transversal direction, it must be, this I must be oriented.
Well, you know, so, okay, I is an interval from 0, 1 with specific parameterization, but frankly, it doesn't matter. I mean, if you take 1 here, then you will get isotopic link with a
-1.
Basically, inverting the vector field will give you the same vector field. So you don't have to worry about it.
There's an isotope in ambient isotope in R3 changing.
Yes, yes. So you don't need to, yes, so you don't need to worry about those details because of this. And so each framed link is also given, can be presented by a diagram. So represented by diagram with what was used to called blackboard diagram, blackboard framing. Which I guess then should have been called whiteboard framing, and now it can be called Zoom board framing. And so, for example, if you see a twist like this, you know, you can really think about it as a picture like that. Yes, if you draw it, you know, that's maybe a good exercise. Take a strip of paper, which looks like this, and flatten it, it will look like this. So in particular, any framing you have is represented by kinks.
Yes.
It's a, I guess I suggested words, but I'm going to talk about
How the blackboard refers to the tech font.
Sorry?
The word blackboard
Yes.
refers to the name of the font in tech.
Oh, I didn't know that.
No, it's a joke because
No, it's not a joke.
not a joke.
It's not a joke. Look.
I know what you mean, but I think it's a joke what you're saying.
No, I'm sure.
Which one?
Yeah, really? Sure, yes.
So
Somebody named it blackboard framing because of MathBB.
probably yes.
Because when you use font MathBB, what you do is kind of you
Or double.
write R or C, you double the legs, right?
Oh, yeah.
And this looks like this. So he claims that it's called blackboard because of math blackboard fonts in LaTeX.
Well, they're all interrelated, yes. It's hard to say what is the chicken, what is the egg here. So we have those framed nodes. Framing is really not a big deal, but it's useful because okay, well, you will see in a moment why it's useful. Diagrams. So maybe a remark that isotopic links or isotopic diagrams related by second Rademeister move. Third Rademeister move. And, well, we cannot use the first Rademeister move, but there is a balanced first Rademeister move. Or framed, I should say, perhaps, first Rademeister move. Okay, so
Okay.
framed R1. Framed Rademeister. Right, so not much of a big deal. And maybe that's a good time to stop.
Okay, let's see if there are any questions. There are many people on Zoom, so if you care to ask a question, just fire it well. Any questions? BJ, any question from Buffalo? No answer. Okay, I don't see any questions from Zoom, so from the room.
I have a question. I have a question about this standard, this Jones construction. If you could come back.
Probably less. Yeah, probably can.
Okay, so this Jones tower is something which is related to this pair, subfactor inside a factor.
Yes.
So what is the purpose of this Jones tower? What does it produce?
Produces it.
For a given pair?
Produces a new polynomial algebra, infinity.
Infinite sequence.
Yes.
Infinite sequence.
When you close it, then you have another algebra.
But what can be said about this system? Why this system is interesting?
Well, I gave you some properties of it.
So we are forgetting about this n. So n disappears from this picture, this subfactor. And we are replacing this by this sequence.
We don't have to do.
Why this sequence is better than this subfactor?
Well, these are, he discovered non-trivial statements. He proved that if the index is finite, then this new M1 is also, this index is finite, that this is 2-1 factor.
And it has the same index, in fact.
Same index. He produced some non-trivial mathematics, which in fact led to some great discovery. It's hard to judge, I guess, what mileage he got out of this in pure phenomenal algebras.
I'm asking because this construction is very similar to the construction in homological algebra. For instance, if you have n in M, you could use this M to construct step by step some resolution of this M, of this subfactor. Okay? So it is very similar, like many constructions in homological algebra. But my question is how this system is related to N.
Well, it's all, of course it is, yes.
It's produced.
Yeah.
With this N, but
I don't know.
What information about this subfactor? Why this question was posed by Jones? Why this question of the subfactor was interesting?
Well, that was his.
And what interesting this construction can say about this subfactor problem?
He studied subfactors. I don't know. I don't know. These are philosophical questions, and I don't know what was his motivation. He was a subfactor guy, as he.
Yeah. So.
But I don't know if I see the analogy with homological algebra. Usually, I would imagine you're talking about taking a model and then considering projected or injected resolution of the model. That's what you mean?
Something, yeah.
But you don't have this. You don't have usually n in M in that context. You just start with a model.
Yeah.
Sequence of.
Heading.
And they sort of different. They have different function. Yes. So those models sort of together describe your initial object, And I don't know if we have this property here. Maybe we do in some sense, but I don't know.
Because these m's are of some type, okay?
All of
Yeah,
them are two one.
Dual,
Yeah.
in this type. Of the same kind.
Yeah.
I would say, okay? And n is sitting in M.
Yeah.
Okay?
To me,
So this, for instance, in homological algebra, you have, for instance, such a problem. You have some, I don't know, some functions which are locally constant, okay? And you are embedding these functions into functions which are continuous.
yeah,
And then you are starting constructing a resolution
that's right.
whose members are, in a sense, continuous or soft sheaves.
In homological algebra, I have one object and I describe it by infinite sequence of simpler objects. Objective, for example, or something.
Mhm.
Yeah, I have one object. I have this inclusion. And then I see that I can I iterate this inclusion and create a tower of objects, which are, to me, are more and more complicated.
Or maybe a stupid question. Could we go back to this slide where
By the way, sorry, Adam, because there's a question from Zoom. In Wenzel theorem, is it from 4 to infinity?
Well, I swear,
Cannot be 4. Because there's a problem with the denominator.
that's right. So I can only say that I look at paper of Jones and he said 3, I'm pretty sure of that. So there is some typo, although, it's, to me, as you said, I mean, it seems like there's some typo, but I don't think it's so essential for the.
Yeah, but the question is about infinity. So when you take arbitrarily large K, right?
Yes.
Okay, that's the point.
Oh, yeah, I see, yes, yeah, to infinite.
Sorry, Adam.
Mhm.
Go ahead.
Okay, so could we go back to the slide with this theorem with these indices?
Jones indices.
Jones indices.
So,
Theorem of Jones. Yes. So we claim that the index of M in M1 is the same as N in M.
yes,
But is it also true that the index of N in M1 would be the same?
no, I don't think so. But yes,
Maybe this somehow addresses your question that you get some sequence of numbers. You can consider index of N in every this.
So what's the
I.
index of M2 over M1? Is it the same?
The same,
True
yes.
would be this.
But
with
adjacent
respect
are
to
the same.
Adjacent, but yes, but you can also ask about index of, for example, N in M3, for example, and this wouldn't necessarily be the same.
That's
And
It's a system.
if it is so, then somehow you produce from this pair M and N
It
infinite
depends.
sequence of numbers.
Yeah,
yes?
but it depends
So you
what.
get some invariant.
Yeah, but it depends on the definition of this Jones index, which I don't
That's a
remember.
funny dimension. It's a dimension in sense I don't understand of is L2 space over von Neumann algebra. But in what sense? But the dimension can be real.
I would like to answer or continue your.
Yeah.
Mhm.
Usually, if you think about these indices, okay, they are transitive. They satisfy something like a cocycle condition.
Yeah.
Okay.
Mhm. I don't know.
So if you're asking
how they
about the index
behave here.
of M5 over M2, for instance, you can compute it from consecutive indices.
Uh-huh.
Yeah, exactly. So like,
Okay, so there is
basically
no additional
information. Exactly.
Yeah.
Exactly. Typical of dimension
Okay.
theory. If dimension of say K in L is 5, and when dimension of something of L is 6, then the dimension of a K is 30.
If
So-
they
so in the-
behave in this way,
Yeah.
there is
There's no information.
So in a sense, it is maybe not a resolution of N. It is a kind of resolution of this index of M over N.
Mhm.
You obtain bigger and bigger algebras,
Mhm.
but these consecutive indices are always the same. Okay? So therefore, my question was, so why this presentation of this index in terms of this sequence of these M's is better than the original presentation of this index as M over N?
I mean, it's not better, but it allows you to construct with M infinity.
So why this an infinity is better?
Yes, I don't know, but at least that's something which is no longer of finite index. And it has some properties which these steps do not have.
And also there is a very.
But the new animals, a new player.
Yeah, but okay, so I'm
And
interested.
also this theory of 2-1 factors is very rich, so maybe it could be used to produce some exotic, I don't know, but maybe it could be.
So 2-1 factors are not closed with respect to these direct limits, these unions.
But yes, as Adam
Because there could be a problem with a trace. For instance.
it's a certain way to construct new L2-1 factors, which I think are exotic. That's at least basic.
So this is about exotic 2-1 factors.
Well, I think in general they're quite exotic, yes.
You definitely get a new and non-trivial phenomenon. What properties it has.
It's worth exploring. What is this? Could you check it for the next time? Or maybe Adam.
Yes.
No,
What was the von Neumann algebraic motivation for Jones?
Yes.
Why this construction is important? What is the purpose of this?
Yes.
I will do my best.
Okay, but I can, and this way we'll wind it up. If I remember correctly, if I'm not mistaken, Wojtek Szymański worked on these towers, and then he proved that a subfactor is when you look at this tower construction, when this higher index for Neumann algebra is a cross product by a finite dimensional Hopf algebra with a subfactor.
Under which assumptions?
I think very much like here.
Very much like it.
Yeah. So that was his thesis.
So this makes this tower
the iteration of cross product.
interesting. Oh yes.
But that's Szymański, not Jones.
Yes. So maybe it will. Yeah.
If I'm not mistaken, yeah, but and these are all cross products, and you shouldn't be surprised that these are cross products because you always have a measurable global section, so there's no hope of non-trivial measurable principal bundle, right? So obviously you wouldn't expect anything more than cross products, right? They're not just sister algebras, they're von Neumann algebras.
They are iterated, cross products,
and he found this Hopf algebra for Jones tower. So that's to me quite spectacular. That is like this. That's a much deeper meaning organizing principle, though generated by M and E1. Yeah, if you say that it's a cross product, you kind of see the fiber. So right, you see the fiber.
What about these groups in these cross products? What are these groups?
Well, these are Hopf algebras, not groups. They are Hopf algebras. This is really Hopf-Galois theory.
And what?
And you can say Hopf-Galois because the fiber is finite dimension.
They come from some corrections, natural corrections of something on something?
I don't know. That's a question for Wojtek Szymański.
Maybe it's related somehow to quantum groups, I don't know.
Well, surely it is this way related to quantum groups.
It will be very
Another homework.
And also,
But I don't know this connection. I know many relations between quantum groups and not theory, but not in this.
But we can discuss it after I stop recording, okay? So
let's save the box.
yes, but then I first stop recording. And
also this projection E1, it is sometimes called condition.